Hello friends, in my this video I am going to discuss about zero padding in DFT. This is very important concept. So let us discuss. So suppose I have one continuous cosine signal like this. Now I want to sample this. Okay. So I have sampled with respect to a particular sampling frequency, and we are getting this kind of sampled version of our signal, of our continuous time signal. After sampling we are getting this particular discrete signal. Now suppose we have only this discrete signal and I am asking you return back the continuous time signal. So what you will do, you will just try to join the successive samples, continuous samples, and we will get this kind of graph, continuous time domain. So if I remove the samples, we will get this kind of continuous time graph after joining all these successive samples of our discrete signal, whatever we have got after sampling. So now you just observe this particular reconstructed continuous signal is not that much looking like cosine signal, although it is we can understand that this is cosine signal, but obviously there are some distortions you can see here like that. So to avoid that, what we do, we increase the sampling rate. That means we increase the sampling frequency, or in other way we can say we decrease the sampling time between two successive samples. And if we now decrease the sampling time or increase the sampling rate, okay, then see the reconstructed signals after joining the successive samples of our new discrete signal, we are getting almost close approximation of our original continuous signal. See this, after joining the samples in the new higher sampling rate signal, we are getting almost same kind of cosine wave as earlier. Okay, so the funda is that decrease the gap between successive samples in time domain, you will have higher resolution, and after reconstruction your signal will almost look like our original continuous time signal before sampling. That's what the simple idea is, what we know. Now same goes for frequency domain. We have discussed in time domain, now let us map the same concept in frequency domain. You know that DFT is sampled version of DTFT. In DTFT we take continuous omega, in DFT we take discrete values of omega, where discrete values are 2 pi by capital N into k, where k takes 0, 1, 2 and so on up to n minus 1. So basically DFT is sampled version of DTFT. This is what we know. Now let us try to write a simple code for plotting the magnitude response for a DTFT signal, and suppose our DTFT signal is this one, cos 2 pi 0.2 into n, and n I am taking from minus 20 to 21. Okay, right? That means total length of n is how much? 42, right? You can clearly understand from minus 20 to 21, that is 42. Okay, so now if I put that formula, that is x of omega equal to summation over n equal to minus infinity to infinity x of n e to the power minus j omega n. The code already I have discussed in my previous video. If you want the detailed explanation of the code, please check the link given in the description. I am not wasting time in explaining the same concept again and again. So this DTFT, if I plot, we will get the magnitude spectrum, one-sided spectrum like this, because I am plotting for omega from 0 to pi, which is our point of interest, right? Because you know that in case of digital or discrete signals, the frequency cannot go beyond pi, because f max is sampling frequency by 2, and when our frequency is equal to sampling frequency by 2, in that time omega equal to pi. This derivation I told while discussing the analog and digital frequency. If you want detailed explanation, again that video link I will post in the description box, go to that. So one-sided spectrum we are getting like this. Now, so we know that DFT is sampled version of DTFT. Let us visualize that. So what I will do, I just extended my code little bit. This plot, up to plot we have done here also, right? Omega comma abs of x of omega. Now what we will do, we will hold on, and in the same figure window we will plot the A50 magnitude part also. So see, n equal to minus 20 to 21. That means how total length is 42. So capital N should be 42 for our DFT, right? And then y equal to A50 of x of n comma 42. N point A50, if we have to compute, we have to write like this: A50 of x of n comma n. Okay, in MATLAB, the A50 is inbuilt function to compute the DFT. Okay. Now here also, while plotting the DTFT spectrum, we have taken our main particular frequency point of interest, that is 0 to pi. Same goes for here. We are plotting single sided DFT, that is 1 to n by 2 plus 1, that is, that is 0 to n by 2 is our main point of interest. So k I am taking from 0 to n by 2, and I am plotting absolute part of y, that is magnitude spectrum of DFT, but instead of taking k, I am taking as frequency in radian. Omega is nothing but 2 pi by n into k. That's what I have written here, 2 pi k by n. Okay. So now if I run this code in MATLAB, I will get this kind of graph. Okay. And from here we can clearly understand that this plot continuous is basically our DTFT, and this stem comment is generating these samples, which are basically our DFT coefficients for various values of omega. And here we can clearly see that DFT coefficients are basically nothing but the sampled version of DTFT. See, all the samples are basically lying on the continuous plot of DTFT. Okay, so from here we can clearly visualize that DFT is sampled version of DTFT. Okay, now see here, our intention or our aim to compute DFT, not to compute DTFT, because in DTFT we take the frequency as continuous, and for a processor, for computer, it is not possible to deal with any continuous signal. So that we compute DFT, and from DFT we try to predict the DTFT, because DFT is nothing but sampled version of our DTFT. So from the sampled version, as I have shown you in time domain, same concept, from the sampled version we can reconstruct our original continuous signal, and we have to do sampling in such a way that after reconstruction the continuous signal should look as much as close to our original continuous signal, right? So we basically have only this DFT plot. We don't have the DTFT. DTFT is continuous. We have the samples which we have computed using some processor or computer, we can say, and now we will join the successive samples to get our continuous waveform, which is DTFT. Okay, just I have written the same code except the DTFT part, as I have shown in my previous slide. So we are getting the magnitude spectrum of DFT like this. Now if I join this, see, the same code I am taking, instead of just stem, I am using plot command. So to join the successive samples, I am doing this. So we can see that our DFT spectrum, if we join successive samples, we are getting the spectrum like this, and this is what is our magnitude spectrum of this particular signal, or we can say DTFT approximation. Now you see one thing very important. We have computed the actual DTFT, what we have seen earlier also, this particular magnitude spectrum, and we have computed DFT, and we have simply reconstructed using the successive samples, and we are getting the reconstructed DTFT like this. Now you tell me whether these two are same. No, they are similar, we can say, but not at all same. There is a huge loss of side lobe information in our reconstructed signal. So this should not happen. What we will do? Same like in time domain, what we have done? Decrease the successive samples while sampling. Okay, that is, increase the sampling frequency or decrease the sampling time. In the time domain I am talking. Now in the frequency domain, when we are in the frequency domain, how we can make this kind of exact DTFT instead of this kind of erroneous DTFT? What we will do? We will increase the sampling rate. Okay, So if DFT is too few points, measured peaks and valleys of f of omega, that is our original DTFT, existing between two DFT points or sampled frequency. As a result, we will lose that particular information and that will not be seen, thus giving us an erroneous view of the spectrum f of omega. As we have seen, this is our original f of omega, but we are getting this one, which is erroneous, right? So what we have to do, what is the remedy? Decrease the gap between successive samples in frequency domain. And you know what we do, how you compute DFT, what is the physical interpretation we have seen. In this particular unit circle, where this is 0, this is pi by 2, this is pi, and this is 3 pi by 2 radian, that is frequency in radian, we take samples as multiple of 2 pi by capital N. That is, first one is 2 pi by capital N into 0, next one is 2 pi by capital N into 1, next one is 2 pi by capital N into 2, and so on. So these are our samples. How many samples we make? We make total n samples. So k varies from 0 to n minus 1. Now you just think, we want to increase this number of samples in the same 0 to 2 pi range. What we will do? Simple. We have to increase the capital N value. So as a result, if we increase the capital N value, what will happen? The successive samples 2 pi by n into 1 and 2 pi by n into 2 will appear closer, so that the gap between two successive samples will decrease. As a result, our information after reconstruction which will not lose as much as earlier. Okay, so we have to increase the n value, because here we are sampling n times. So if we increase the n, more number of samples we will get in the same duration. So as a result, we can reconstruct more accurately and get back our original signal. Okay, but there is a problem. We cannot simply increase our capital N value. Why? Suppose our original time domain signal is having 54 samples, but we want to compute DFT for capital N equal to 64. But what you know, small n and k should lie in the same range 0 to capital N minus 1. K is okay, 0 to capital N minus 1, so 0 to 64 minus 1, that is 0 to 63, it will align. But what about small n? Small n in time domain is simply, we are having 54 samples, so small n is only 0 to 53. We cannot change this one, na? So what we will do? We cannot simply increase capital N value. By simply increasing capital N, it will increase k from 0 to n minus 1, that is okay. But what about time domain? 0 to 53 only we will have. What about the rest part from 54 to 63? Simple. If we have nothing in the time domain, but we require something, what we will do? Simply pad zeros in that. So we will pad zeros in that part. So suppose my time domain signal is 0 to 54, 0 to 53, small n range. Now I want to compute DFT for 64. That means I require in time domain, I require the original signal from 0 to 63, but I am having from 0 to 54. So for rest of the part, what I will do, I will add required number of zeros. Like here you can see our sine signal is there. And if we want to compute for more number of DFT than our time sample range in the time domain, we have to add required number of zeros at the end. Simple, right? From simple concept we can say, this is simple idea, general idea, from general knowledge we can say that, okay, if nothing is there, we will add 0. Simple, right? As simple as that. Now, in MATLAB, when you are going to compute this zero padding, you no need to do anything. Because if you go to FFT function, which is present in MATLAB, here it is clearly written, if x vector and length of x is greater than, see this one, if x is a vector and length of x is less than n, then x is padded with trailing zeros to length n. That means if our x, which is our signal original time domain signal, if it is having length lesser than the n point DFT, n is the number which point DFT we want to compute, then MATLAB this particular FFT command will simply pad required number of zeros at the end, so that it is trailing zeros to length of n. So total length it will take care of. So now let's verify. Simple MATLAB code. Again, time sample, same signal I have taken, that is minus 20 to 21, x of n is equal to cos 2 pi 0.2 into n. But now we want to compute, instead of 42, we want to compute DFT for 512. Okay? And same, rest of the code is also same, just single sided DFT we want to plot. So now if you run the code, you will get the magnitude spectrum of DFT like this. Okay? Now instead of stem, as we want our continuous domain representation, because DTFT is continuous, so we have to join the successive samples of DFT. So instead of stem, write plot, and the same rest of the code remains unchanged. So if I do plot, I will get the waveform like this. And now consider, this is our DTFT, this is our magnitude response from original DTFT code what we achieved. This is the magnitude response after joining the successive samples of DFT. That is, we have got sample and we have successively joined them. Now see, side lobe also we are getting information. So basically, what we are achieving, that with increase in capital N, we in the DFT we are getting almost close approximation of our DTFT. This is why what I want to say. So this is the concept of zero padding. Now, very important concept. Often students misunderstand this. That zero padding, without zero padding we were not getting side lobes, but with zero padding we are getting side lobes. That means we are getting more information about the signal after zero padding. No, not at all. This is wrong concept. Understand it very clearly. Without zero padding, that means when you are doing sampling with a high interval, we were basically not getting the information what we already have. The information we already have, but we were sampling, the sampling interval was such that we were not getting some information between two successive samples. That means what we have, we were not utilizing the complete part of that. But now after zero padding, what we have, we are utilizing complete part of that. We are taking successive samples gap very small, so that we can extract as much as information from what we have. From what we don't have, we are not getting any information. The information we already have, but we were not getting due to low sampling rate in the frequency domain. But due to increased value of n, as the sampling increases, sampling interval decreases, or we can say as capital N increases, we are doing more samples in the same time. So as a result, what is happening, we are getting complete information from the part what we have. We are not getting any information what we previously don't had, right? So basically, as the zero padding increases, the DFT spectrum approaches towards the continuous spectrum, and due to zero padding, we are not getting any excess information. This simply you can achieve like this. So that's what I have written here. No new information is added to the signal, only additional zeros are added to our output data. Very simple. If you want to cross verify, you write the code CLC clear all close all, define the time sample range and our discrete time signal, and compute the 512 FFT, that is increased value of n FFT you compute, and take inverse FFT and plot the signal. What you will get in the original data, our original data was this much previously, but apart from padding of zeros in the tail, we are not getting anything, and this is not any information, right? This is only simple zeros what we are getting after the end of our original data. We are not getting any additional information due to zero padding. This is also very important concept. So what we conclude from our this discussion, what we have understood, number one, we have visualized that DFT is nothing but sampled version of DTFT. Number two, if we want to get exact representation of DTFT, or if we want to reconstruct the DTFT from DFT, we have to do zero padding. That means we have to do or compute the FFT for higher value of n. Okay, so this is very important concept. This is all for my this video. Thank you for watching.